Tonight, look up. If you're away from city lights, if the sky is clear and the moon isn't too bright, you might catch it. A faint smudge of light in the constellation Andromeda. It doesn't look like much at first glance. Just a small, fuzzy patch that you might mistake for a distant cloud or trick of your vision. But that pale glow is something extraordinary. It's another galaxy. The only one you can see with your naked eye from the northern hemisphere tonight. And right now, the light reaching your eyes left that galaxy 2.5 million years ago. Before humans existed, before we walked upright, before we made tools or language or fire. That light has been traveling through empty space for longer than our species has been alive, and it arrived just in time for you to see it. We call it Andromeda, and it's our nearest large galactic neighbor. But calling it a neighbor feels almost too casual, doesn't it? Like it lives down the street instead of 2.5 million light-years away. Yet compared to the rest of the universe, Andromeda is practically next door. It's close enough that we can study individual stars within it. Close enough that we can map its structure, trace its history, and predict its future. And close enough that one day, billions of years from now, it will collide with our own Milky Way in one of the most spectacular cosmic events imaginable. But before we get to that future collision, let's talk about finding Andromeda tonight. It's not difficult once you know where to look. First, find the constellation Cassiopeia. It looks like a big letter W or M, depending on the time of year, sitting in the northern sky. From there, trace a line down toward the constellation Andromeda itself. You're looking for 3 stars in a row that form part of Andromeda's body. From the middle star, look slightly upward. That's where the galaxy sits. With your naked eye, it appears as a faint oval smudge. If you have binoculars, even cheap ones, suddenly it becomes more impressive. You can see its elongated shape, the brighter core, hints of the structure that makes it what it is. Light pollution is the enemy here. If you're in a city, you probably won't see it at all. But drive 30 minutes away from urban lights. Let your eyes adjust to the darkness for 15 minutes, and suddenly, Andromeda emerges. A ghost in the night sky. A reminder that we're not alone in the universe, not isolated in our single galaxy, but part of a cosmic neighborhood where galaxies exist by the trillions. What's remarkable about seeing Andromeda with your own eyes is the time travel involved. That light left its galaxy before the first humans appeared in Africa. It traveled through the void while our ancestors evolved, while continents shifted, while ice ages came and went. It crossed 2.5 million light-years of empty space at the fastest speed anything can travel, and it arrived here tonight so you could see it. When you look at Andromeda, you're not seeing it as it is now. You're seeing it as it was in the deep past. Whatever is happening there right now, we won't know about it for another 2.5 million years. So let's talk about what we do know. Because over the past century, and especially in the last few years, we've learned that Andromeda is far stranger, more violent, and more massive than anyone imagined. It's not just another spiral galaxy like ours. It's bigger, more active, and it's been through cosmic battles that would have destroyed smaller galaxies entirely. This is the story of our nearest neighbor, the only large galaxy we can see face on. The mirror that helps us understand our own Milky Way, and the future collision partner that will one day merge with us to create something entirely new. For most of the 20th century, astronomers thought they had Andromeda figured out. It was a spiral galaxy, similar to the Milky Way, sitting comfortably in our cosmic neighborhood. We measured its size, counted its stars, and assumed we understood what we were looking at. Then, in the late 2010s and early 2020s, new data started coming in that changed everything. Andromeda wasn't the galaxy we thought we knew. It was far larger, far more violent, and far more complex. The first surprise came from mapping its outer regions. For decades, we assumed Andromeda's visible disk extended about 110,000 light-years across, making it slightly larger than the Milky Way. But when astronomers started looking more carefully at the faint outer regions using sensitive instruments, they found something unexpected. Stars. Lots of them. Scattered far beyond where the galaxy was supposed to end. These weren't random stragglers. They were organized into faint streams and shells, the telltale signs of ancient collisions. And they extended the galaxy's true diameter to over 220,000 light-years. In other words, Andromeda is actually twice as wide as we thought just a few years ago. This discovery fundamentally changed how we think about galactic size. Galaxies don't have hard edges like planets do. They fade gradually into space, and defining where one ends and the intergalactic void begins is surprisingly difficult. But these faint outer stars are still gravitationally bound to Andromeda. They orbit its center. They're part of the system. Which means Andromeda is genuinely enormous, dwarfing our own Milky Way in physical size. But size is just one measurement. What about the stars themselves? How many stars does Andromeda actually contain? For years, estimates put the number at around 1 trillion stars, roughly the same as the Milky Way, or perhaps slightly more. Recent surveys using data from the Hubble Space Telescope and the James Webb Space Telescope have refined this estimate. The current best guess is that Andromeda contains somewhere between 1 trillion and 1.5 trillion stars. That's significantly more than our galaxy, which has perhaps 200 to 400 billion stars depending on which estimate you trust. More stars means more mass, more gravity, and more history. Every one of those trillion-plus stars has a story. Some formed billions of years ago in the galaxy's youth. Others are being born right now in vast clouds of gas and dust. And the sheer number of them means Andromeda is gravitationally dominant in our local region of space. It's the largest galaxy in the local group, the collection of about 80 galaxies that includes the Milky Way, Triangulum, and dozens of smaller dwarf galaxies. Andromeda is the anchor. Everything else orbits around it, or will eventually be consumed by it. Now, let's talk about star formation. This is where things get really interesting. You might think that a galaxy as old as Andromeda, which has been around for over 10 billion years, would be settling down, running out of gas, and forming new stars at a slower rate. Yet despite its age, Andromeda is still forming new stars at a steady rate, with enormous reservoirs of gas left over from its turbulent history, fueling fresh bursts that surprise astronomers who expected it to be winding down. Why is Andromeda forming stars so vigorously? The answer lies in its turbulent history. When galaxies collide, or when a large galaxy consumes smaller companions, the gravitational interactions compress gas clouds. This compression triggers massive bursts of star formation. Andromeda has been through multiple collisions in the last few billion years, and it's still recovering. Those ancient impacts left scars in the form of tidal streams and warped structures, but they also left behind enormous reservoirs of gas that are still collapsing into stars today. One of the most impressive star-forming regions in Andromeda is called NGC 206. This isn't just a notable region within Andromeda. It's the largest single starbirth complex in the entire local group. Think about that for a moment. Out of all the galaxies in our cosmic neighborhood, the most massive active star-forming region is in Andromeda. NGC 206 is a stellar nursery on a scale we don't have anything to compare it to in the Milky Way. It contains thousands of young, hot, massive stars that formed within the last few million years. These stars are so bright and energetic that they light up the surrounding gas, creating glowing clouds visible even across millions of light years. The stars being born in NGC 206 aren't like our Sun. Many of them are massive, weighing 10, 20, or even 50 times what the Sun weighs. These stars burn incredibly hot and bright, but they also die young. They'll only live a few million years before exhausting their fuel and exploding as supernovas. When they do, they'll scatter newly created elements across Andromeda, enriching the gas from which future stars will form. This is the cycle of stellar life and death, and in NGC 206, we're watching it happen on a massive scale. The recent high-resolution mosaics from Hubble and the James Webb Space Telescope have revealed just how chaotic Andromeda's structure really is. When astronomers piece together hundreds of individual images to create a full portrait of the galaxy, what emerges is not a clean, orderly spiral. It's a train wreck. That's the term some researchers use, and it's surprisingly accurate. Andromeda looks like a galaxy that's been through a series of collisions and is still settling from its chaotic youth. You can see this chaos in the massive dust lanes that cut across the galaxy's disk. These aren't neat spiral arms like you might expect. They're thick, irregular bands of dust and gas that have been stirred up and rearranged by gravitational interactions. In some regions, the dust lanes twist and buckle in ways that make no sense unless you account for past mergers. And scattered throughout the disk are streams of stars, long rivers of suns that trace the paths of smaller galaxies that Andromeda consumed. The evidence suggests that Andromeda has eaten several large galaxies in the last few billion years. Not just tiny dwarf galaxies, which get consumed all the time, but substantial systems with billions of stars. When these galaxies fell into Andromeda, they didn't merge cleanly. They were torn apart by tidal forces, their stars scattered along their orbital paths, creating the streams and shells we see today. Some of these streams wrap completely around Andromeda, visible as faint arcs of stars against the darkness. Think of it like this. Imagine dropping a handful of sand into a pond. The grains don't all sink to the bottom in one spot. They spread out, following currents, dispersing across the water. That's what happens when a dwarf galaxy falls into Andromeda. The galaxy gets stretched by tidal forces, its stars following different paths, spreading out along its orbit until what was once a compact system becomes a long stream wrapping around the larger galaxy. And the outer disk is still warped. If you look at Andromeda edge-on in certain wavelengths, you can see that the disk doesn't lie flat. It ripples and bends, like a warped record. This warping is direct evidence of those ancient collisions. When a smaller galaxy passes through Andromeda's disk, it creates gravitational waves that propagate outward through the structure, causing it to buckle and twist. These waves take billions of years to settle down, which means we're seeing Andromeda still ringing like a bell from impacts that happened in the deep past. All of this violence, all of this chaos, tells us something important. Andromeda is not a peaceful spiral galaxy quietly aging in space. It's a dynamic, evolving system that has grown through conquest. It's a survivor of cosmic battles that would have destroyed smaller galaxies. And it's still digesting the remnants of its victims, still forming stars from their stolen gas, still carrying the scars of old mergers after billions of years. The Milky Way, by comparison, has had a relatively quiet history. We've consumed our share of dwarf galaxies, but we haven't been through the kind of major mergers that Andromeda has experienced. This makes Andromeda an incredibly valuable object to study. By looking at our neighbor, we can see what happens when a large spiral galaxy goes through violent growth. We can trace the scars left by ancient collisions. And we can predict what might happen when Andromeda and the Milky Way eventually collide billions of years from now. But Andromeda's violence isn't just ancient history, it's ongoing. Right now, as you read this, Andromeda is pulling in smaller satellite galaxies, tearing them apart and absorbing their stars. This process happens continuously in large galaxies, It's how they grow. Every major galaxy we can observe is surrounded by a halo of smaller companions, and over time, those companions spiral inward and are consumed. Andromeda is particularly aggressive in this regard. It has more satellite galaxies than the Milky Way, and it's been more efficient at capturing and destroying them. The dust lanes we mentioned earlier are also sites of active star formation. When you look at Andromeda in infrared wavelengths, which can penetrate dust, those dark lanes light up with the glow of forming stars. Massive clouds of molecular hydrogen are collapsing under their own gravity, fragmenting into thousands of stellar embryos. Within a few million years, these will ignite as new suns, adding to Andromeda's already enormous stellar population. And here's something that really drives home the scale. If you could somehow travel to Andromeda and visit one of these star-forming regions, you'd find yourself in an environment completely unlike anything in our solar neighborhood. The gas clouds would be vast, beyond comprehension, spanning hundreds of light years. The young stars would be scattered throughout, some still embedded in their birth clouds, others having blown away the surrounding material with their intense radiation. The whole region would glow with the light of thousands of newborn suns, and the temperature would range from near absolute zero in the densest cloud cores to millions of degrees in the hot bubbles carved out by stellar winds and supernova explosions. Let's focus on NGC 206 for a moment because it really is extraordinary. This region alone contains enough material to form hundreds of thousands of stars. The gas density there is hundreds of times higher than the average density in the galactic disk. When you compress gas like that, gravity takes over more easily. Clumps form, those clumps collapse, and stars ignite. The process happens relatively quickly in cosmic terms. A massive cloud like the one in NGC 206 can form an entire cluster of stars in just a few million years. What makes NGC 206 even more remarkable is that we can watch different stages of star formation happening simultaneously. In some regions, the gas is still cold and dark, barely beginning to collapse. In other regions, protostars have formed, glowing faintly in infrared light as they gather more material. And in yet other regions, massive young stars have already ignited, blasting their surroundings with ultraviolet radiation and stellar winds that are starting to disperse the remaining gas. The most massive stars in NGC 206 are genuine monsters. Some weigh 50 or even 100 times what the Sun weighs. These stars are incredibly rare. For every star this massive, there might be thousands of smaller stars like the Sun. But the massive ones dominate the region. They're so bright that a single one can outshine a million suns. They're so hot that their surfaces reach temperatures of 40,000 degrees or more, compared to the Sun's relatively cool 5,500 degrees. But these massive stars are also doomed. They burn through their fuel at an incredible rate. A star like the Sun will live for 10 billion years. A star weighing 50 times the Sun's mass will live only a few million years. It's like the difference between a candle that burns for hours and a firework that explodes in seconds. The massive stars are cosmic fireworks, brilliant and brief. Let's focus on NGC 206 for a moment because it really is extraordinary. This region alone contains enough material to form hundreds of thousands of stars. The gas density there is hundreds of times higher than the average density in the galactic disk. When you compress gas like that, gravity takes over more easily. Clumps form, those clumps collapse, and stars ignite. The process happens relatively quickly in cosmic terms. A massive cloud like the one in NGC 206 can form an entire cluster of stars in just a few million years. What makes NGC 206 even more remarkable is that we can watch different stages of star formation happening simultaneously. In some regions, the gas is still cold and dark, barely beginning to collapse. In other regions, protostars have formed, glowing faintly in infrared light as they gather more material. And in yet other regions, massive young stars have already ignited, blasting their surroundings with ultraviolet radiation and stellar winds that are starting to disperse the remaining gas. The most massive stars in NGC 206 are genuine monsters. Some weigh 50 or even 100 times what the Sun weighs. These stars are incredibly rare. For every star this massive, there might be thousands of smaller stars like the Sun. But the massive ones dominate the region. They're so bright that a single one can outshine 1,000,000 suns. They're so hot that their surfaces reach temperatures of 40,000 degrees or more compared to the Sun's relatively cool 5,500 degrees. But these massive stars are also doomed. They burn through their fuel at an incredible rate. A star like the Sun will live for 10 billion years. A star weighing 50 times the Sun's mass will live only a few million years. It's like the difference between a candle that burns for hours and a firework that explodes in seconds. The massive stars are cosmic fireworks, brilliant and brief. When these stars die, they don't fade quietly. They explode as supernovas, some of the most violent events in the universe. The explosion releases more energy in a few seconds than the Sun will produce in its entire 10 billion-year lifetime. The blast wave tears through the surrounding gas at thousands of kilometers per second, heating it to millions of degrees, creating expanding bubbles of superhot plasma. And here's the beautiful part. Those supernovas create new elements. The intense heat and pressure during the explosion fuse atoms together, creating everything from carbon and oxygen to iron and gold. These newly created elements get scattered across hundreds of light years, mixing with the existing gas, enriching it. The next generation of stars that forms from this enriched gas will have more heavy elements. And planets that form around those stars will have more raw materials for complex chemistry and life. So NGC 206 isn't just forming stars, it's also seeding Andromeda with the building blocks of planets and life. The same process happened in the Milky Way billions of years ago. The heavy elements in your body, the iron in your blood, the calcium in your bones, they were all created in supernova explosions in ancient star-forming regions, not unlike NGC 206. These star-forming regions are also where planets are born. Around each young star, a disk of leftover material orbits, gradually clumping together to form planets. In Andromeda right now, millions of planetary systems are in the process of forming. Rocky planets like Earth, gas giants like Jupiter, ice worlds like Neptune, and probably countless types of planets we haven't even imagined because we've only studied our own solar system and a few thousand exoplanets in detail. The James Webb Space Telescope has started to peer into these star-forming regions in unprecedented detail. Its infrared vision can penetrate the thick dust that blocks visible light, revealing the protostars hidden within. In some regions of Andromeda, Webb has detected dozens of protostars clustered together, each one surrounded by a disk of material that will eventually form planets. These observations are revolutionizing our understanding of how planetary systems form, not just in our galaxy, but in other galaxies as well. What's particularly exciting is that some of these planetary disks show gaps and rings, structures that indicate planets are already forming. A massive planet orbiting close to its star can clear a gap in the disk, sweeping up material along its orbital path. We can't see these planets directly. They're too small and too faint, but we can see their gravitational influence on the surrounding disk. It's like seeing footprints in the snow and knowing someone walked there, even if you can't see the person. The diversity of planetary systems is staggering. In our own galaxy, we've found hot Jupiters, massive gas giants orbiting incredibly close to their stars. We've found super-Earths, rocky planets larger than Earth but smaller than Neptune. We found systems with multiple planets in resonant orbits, where their periods are related by simple ratios. And we've found planets in the habitable zone, the region where liquid water could exist on a surface. All of these types probably exist in Andromeda as well. With over 1 trillion stars, and assuming most of them have planets, Andromeda might contain trillions of planets. Some will be lifeless rocks, too hot or too cold for life. But statistically, some must be Earth-like, with liquid water, stable climates, and the chemical ingredients for life. Whether life has actually emerged on any of these worlds is unknown. But the raw numbers suggest it's at least possible. Take a breath. Right now, 2.5 million light-years away, stars are being born in Andromeda. Planets are probably forming around some of those stars. And if life exists there, if anyone is looking up at their night sky tonight, they might be seeing our Milky Way as a faint smudge in their own constellation patterns. They'd be seeing us as we were 2.5 million years ago, just as we see them in their distant past. The light takes so long to travel that we're always looking at each other's history, never the present. Every large galaxy has a dark matter halo. We can't see dark matter directly, but we know it's there because of its gravitational effects. It holds galaxies together, provides the gravitational scaffolding around which visible matter clusters, and extends far beyond the visible stars and gas. For Andromeda, recent measurements have revealed that this dark matter halo is even more massive than we thought. It's 20 to 30% larger than estimates from just a year or two ago, extending perhaps 1 million light-years from the galaxy's center. This revised size comes from studying the motions of Andromeda's satellite galaxies. These small companions orbit Andromeda at various distances, and by measuring their speeds and trajectories, astronomers can infer how much mass is pulling on them. The fact that distant satellites are moving faster than expected tells us there's more mass present, and since we can't see enough visible matter to account for it, that mass must be dark matter. Think of dark matter like an invisible ocean. The visible galaxy, all those stars and gas clouds we can see, is like foam floating on the surface. The foam is what catches your eye, but the real mass is in the water beneath, the dark matter that makes up most of the galaxy's gravitational presence. And just like an ocean, this dark matter extends far beyond where the visible matter ends. But here's where things get strange. When you look at the distribution of Andromeda's satellite galaxies, they're not scattered randomly around the galaxy as you might expect. About half of them orbit in a single thin plane, like a giant rotating disk of dwarf galaxies encircling Andromeda. This is called the Great Plane of Andromeda, and we still don't have a good explanation for it. In a standard model of galaxy formation, satellite galaxies should come from all directions, falling into the primary galaxy along random paths. They should form a roughly spherical cloud around the main galaxy. But in Andromeda, we see this highly organized structure instead. The satellites move coherently, orbiting in the same direction, confined to a plane that's only about 40,000 light-years thick, but extends for hundreds of thousands of light-years. It's like they were all captured at the same time from the same source, or formed together in some way we don't understand. The Milky Way has a similar structure, which we call the vast polar structure. But seeing it in Andromeda confirms this isn't just a quirk of our own galaxy. It seems to be a common feature, which suggests something fundamental about how large galaxies and their satellites form and interact. Some theories propose that these planes are the remnants of filaments in the cosmic web, the large-scale structure of the universe. Picture the universe as a giant spider web with galaxies forming where the strands intersect. When a large galaxy forms at one of these intersections, it might preferentially capture smaller galaxies from along one particular filament, creating this planar distribution we observe. Others suggest they form when a large galaxy consumes a medium-sized one, and that galaxy's own satellites become satellites of the larger system, preserving their original orbital plane. Imagine Andromeda swallowing a galaxy about a tenth its size, a galaxy that had its own small satellites orbiting it. After the merger, those satellites would still be orbiting, but now they'd be orbiting Andromeda instead of their original host. And they'd maintain their original orbital plane, creating this strange structure we observe. One of the most fascinating recent discoveries is a satellite galaxy called Pegasus VII. This is what astronomers call an ultra-faint dwarf galaxy, meaning it contains very few stars and is incredibly difficult to detect. Pegasus 7 is special because it appears to be a pristine relic, a galaxy that formed in the early universe and has barely changed since. It's only just now falling into Andromeda's gravitational influence for the first time. Why is this important? Because most satellite galaxies have already been affected by their host galaxy's gravity. They've lost gas, they've been distorted by tidal forces, and their star formation has been shut down. But Pegasus VII is different. It's still relatively intact, still contains its original gas, and hasn't been significantly altered by Andromeda. This makes it a window into the early universe, a fossil from a time when galaxies were just beginning to form. Studying Pegasus 7 and galaxies like it helps us understand what the first dwarf galaxies looked like, how they formed, and what their chemical composition was. The stars in Pegasus 7 are extremely metal-poor, meaning they contain very few elements heavier than hydrogen and helium. This tells us they formed from gas that hadn't been enriched by many previous generations of stars. They're among the oldest stars we can observe, and they carry information about conditions in the universe billions of years ago. When we say metal poor, we're using the astronomers' definition of metal, which is any element heavier than helium. So carbon, nitrogen, oxygen, iron, everything you think of as making up planets and people, astronomers call metals. The first stars in the universe had almost no metals at all. They formed from pure hydrogen and helium left over from the Big Bang. When those stars died, they scattered newly created elements into space, enriching the gas from which the next generation would form. This process has been happening for over 13 billion years, gradually making the universe more metal-rich. But galaxies like Pegasus 7 that formed early and have been isolated ever since still preserve the low metallicity of the ancient universe. But most of Andromeda's satellites haven't been so lucky. The galaxy has devoured more companions than the Milky Way has, and its halo is stuffed with tidal debris from these ancient collisions. When you look at Andromeda in very deep exposures that can detect extremely faint structures, you see what astronomers call ghost streams. These are faint ribbons of stars that wrap around the galaxy, the scattered remains of dwarf galaxies that were torn apart millions or billions of years ago. Each stream tells a story. By tracing its path and measuring the properties of its stars, astronomers can reconstruct when the collision happened, how massive the dwarf galaxy was, and what trajectory it followed as it fell into Andromeda. Some streams are thick and well-defined, indicating relatively recent destruction. Others are thin and diffuse, spread out over vast regions of space, indicating they came from galaxies that were consumed billions of years ago and have had time to disperse. One of the streams is particularly massive, suggesting it came from a galaxy with perhaps a billion stars. This wasn't a minor dwarf. It was a substantial system, and Andromeda destroyed it completely, scattering its stars across hundreds of thousands of light years. These stars are now part of Andromeda's halo, indistinguishable from stars that formed in Andromeda itself, except for their unusual orbits and slightly different chemical compositions. When a dwarf galaxy is torn apart, its stars don't just vanish. They continue orbiting Andromeda, but now they're spread out along the path the dwarf galaxy followed. If you could watch this process in fast forward over millions of years, you'd see the dwarf galaxy stretched like taffy, becoming longer and thinner as tidal forces pull it apart, until eventually it's just a stream of individual stars wrapping around Andromeda multiple times. The physics of tidal disruption is fascinating and worth understanding. Tidal forces arise because gravity weakens with distance. The side of a dwarf galaxy closest to Andromeda experiences stronger gravitational pull than the far side. This difference in pull stretches the galaxy. At first, the dwarf's own gravity is strong enough to hold it together. But as it gets closer to Andromeda, the tidal forces increase. Eventually, they overcome the dwarf's self-gravity, and the galaxy starts to come apart. The process is gradual. On the first passage through Andromeda, the dwarf might lose only its outermost stars. On subsequent passages, more and more material gets stripped away. The core, where stars are most densely packed, is the last to go. This can continue for billions of years, with the dwarf making multiple orbits before finally being completely dissolved. What's remarkable is that we can actually see this process frozen at different stages. Some of Andromeda's satellites are intact, showing no signs of disruption. Others show tidal tails, streams of stars being pulled away but still partially attached. And still others have been completely shredded, leaving only the ghost streams we've been discussing. It's like looking at a series of photographs showing the life cycle of a dwarf galaxy from capture to destruction. The dark matter component of these dwarfs is also affected by tidal forces, but in a different way. Dark matter doesn't interact with itself or with normal matter except through gravity. So when a dwarf galaxy gets torn apart, its dark matter halo also gets stretched and dispersed. These dark matter streams are completely invisible, but they're there, threading through Andromeda's halo alongside the visible stellar streams. Detecting these dark matter streams is incredibly challenging. We can't see them directly, but we can infer their presence by looking for gravitational effects. If a dark matter stream passes near a stellar stream, it can create perturbations, small kinks, or gaps in the stellar stream. By mapping these perturbations in detail, astronomers can work backwards to figure out where the dark matter is. This technique has revealed that Andromeda's halo is far more structured than we thought. It's not a smooth distribution of dark matter. It's lumpy, filled with subhalos and streams from past mergers. Each lump represents the dark matter halo of a dwarf galaxy that Andromeda consumed. These subhalos can persist for billions of years after the visible galaxy has been completely destroyed. The Great Plane of Andromeda, that strange planar distribution of satellites, is even more puzzling when you consider the dark matter. The satellites in the plane are moving coherently, all orbiting in the same direction. This suggests they came from a common source. One possibility is that they're all remnants of a single large merger. Imagine Andromeda consuming a galaxy perhaps a tenth its mass. That galaxy would have had its own satellites, maybe a dozen or more small dwarfs orbiting it. After the merger, those satellites would become Andromeda's satellites, but they'd preserve their original orbital plane. This could explain the structure we observe. Another theory involves the cosmic web. The universe isn't uniform. It's organized into filaments and nodes, with galaxies forming where filaments intersect. If Andromeda formed at the intersection of several filaments, it might have preferentially accreted material from along one particular filament. The dwarf galaxies that fell in along this filament would naturally form a planar structure, all arriving from roughly the same direction. Testing these theories requires detailed simulations. Astronomers use supercomputers to model galaxy formation and evolution, starting from the early universe and running forward billions of years. These simulations can predict what patterns we should see in satellite distributions for different formation scenarios. By comparing the predictions to observations, we can start to narrow down which theories are most likely correct. The discovery of Pegasus VII has added another piece to this puzzle. As a pristine dwarf that's only just falling in, it can tell us about the population of dwarf galaxies in the early universe. How common were galaxies like this? How did they form? And how many of them have already been consumed by larger galaxies like Andromeda? Studying Pegasus 7's stars reveals that they formed over 10 billion years ago when the universe was less than a quarter of its current age. The gas from which these stars formed was almost pure hydrogen and helium, with only trace amounts of heavier elements. This low metallicity is a signature of the early universe, before many generations of stars had lived and died to enrich the gas with heavy elements. The fact that Pegasus 7 has survived intact for so long is also informative. It tells us that the dwarf must have formed in a relatively quiet region of space, far from larger galaxies that would have disrupted it. It's been orbiting in the outskirts of the local group, slowly falling toward Andromeda, but only now getting close enough to be significantly affected by the larger galaxy's gravity. In a few billion years, Pegasus VII will share the fate of so many other dwarfs. It will be pulled apart by tidal forces, its stars scattered into a stream, its dark matter dispersed into Andromeda's halo. But for now, it survives, a relic of the early universe, a window into conditions 13 billion years ago. Then there's M32, one of Andromeda's most peculiar companions. M32 is a compact elliptical galaxy, small but incredibly dense. It contains about 3 billion stars packed into a volume only a few thousand light-years across. This makes it one of the densest galaxies we know. The stars in M32 are so tightly packed that if you lived on a planet there, your night sky would be filled with stars bright enough to read by. There would be no true darkness. The mystery of M32 is that it shouldn't exist in its current form. Galaxies this dense are usually much larger, and M32 is too small to have formed naturally with such a high density. The leading theory is that M32 was once a much larger spiral or elliptical galaxy, perhaps comparable in size to the Milky Way. But at some point, it had a close encounter with Andromeda. The tidal forces from that encounter stripped away most of M32's outer stars and gas, leaving only the dense central core. What we see today is the stripped-down remnant of a galaxy that Andromeda partially cannibalized. There's even evidence that this encounter happened relatively recently in cosmic terms, perhaps within the last few billion years. Some of the tidal streams around Andromeda may have come from M32 during this interaction. And M32 itself is still orbiting Andromeda, still being affected by its gravity, possibly on a path that will eventually cause it to merge completely with the larger galaxy. If this theory is correct, then M32 is a cautionary tale. It was once a proper galaxy in its own right, possibly with spiral arms and active star formation. But it wandered too close to Andromeda, and that proximity was its doom. The larger galaxy's gravity tore away its outer regions, shut down its star formation by stripping away its gas, and left behind only the core. In another few billion years, even that core might be consumed. All of these satellite galaxies, these streams, this halo of debris, they paint a picture of Andromeda as a cosmic predator. It's been growing through consumption for billions of years, pulling in smaller galaxies, tearing them apart, and adding their stars to its own population. This is how large galaxies evolve. They don't form in isolation and remain unchanged. They grow through mergers, through accretion, through the gradual accumulation of smaller systems. Andromeda is particularly good at this. It's the dominant gravitational force in the local group, and everything nearby is either already part of it or will be eventually. The dark matter halo plays a crucial role in this process. It's the gravitational net that captures passing galaxies, slowing them down and pulling them into orbits that eventually decay. The halo extends so far beyond the visible galaxy that smaller systems can be captured from enormous distances. Once caught in the halo's gravity well, escape is nearly impossible. The satellite spirals inward over hundreds of millions of years, passes through Andromeda's disk, loses mass and energy with each passage, and eventually merges completely. Some of Andromeda's current satellites are doomed. We can already predict their fates based on their current orbits. They'll spiral inward over the next few billion years, contributing their stars and gas to Andromeda's continued growth. The ghost streams we see today will be joined by new streams from galaxies being destroyed right now. And billions of years in the future, when the Milky Way and Andromeda collide, the combined system will have an even richer halo filled with the debris of dozens of consumed galaxies. At the center of Andromeda, hidden behind layers of stars and dust, sits a supermassive black hole. This isn't unusual. Nearly every large galaxy has one, a gravitational monster containing millions or billions of times the Sun's mass compressed into a region smaller than our solar system. But Andromeda's black hole is special for a few reasons. First, it's genuinely massive, weighing in at somewhere between 100 and 200 million times the Sun's mass. That makes it significantly larger than Sagittarius A star, the black hole at the center of the Milky Way, which is only about 4 million solar masses. Second, and perhaps more surprisingly, Andromeda's black hole is strangely quiet. Despite its enormous mass, it's not actively consuming large amounts of matter right now. Black holes can be detected when they feed because the infalling matter heats up to millions of degrees and emits intense radiation across the electromagnetic spectrum. Active black holes shine brightly in X-rays and can outshine their entire host galaxies. But Andromeda's black hole is dim, sipping only small amounts of gas, producing relatively faint emissions. This raises an interesting question. Why is such a massive black hole so quiet? The answer probably lies in the availability of fuel. Black holes can only consume matter that falls close enough to be captured by their gravity. If there's not much gas or dust near the galactic center, the black hole starves. Andromeda's central region has been swept relatively clean by past activity, and current star formation is concentrated in the disk rather than the core. So the black hole waits, dormant, like a sleeping giant. But it wasn't always quiet. Recent X-ray observations from NASA's Chandra Observatory and ESA's XMM Newton satellite have revealed faint lobes of high-energy emission extending above and below Andromeda's central plane. These structures are similar to the Fermi bubbles discovered in the Milky Way, enormous balloons of hot gas and cosmic rays extending tens of thousands of light-years from the galactic center. Their discovery in Andromeda was announced in 2025, adding another piece to the puzzle of the galaxy's violent past. These lobes are evidence that Andromeda's black hole had violent outbursts millions of years ago. During these episodes, the black hole consumed enormous amounts of matter, perhaps when a gas cloud or even a star wandered too close. The intense energy released during feeding created jets of particles and radiation that blasted outward from the galactic center, carving out these bubbles in the surrounding gas. The structures we see today are the fading echoes of that ancient violence. The timescale for these outbursts is uncertain, but the fact that we can still detect them suggests they happened within the last few million years, relatively recently in cosmic terms. It's possible that Andromeda's black hole undergoes periodic episodes of activity, flaring up when fresh fuel becomes available, then going dormant again when the cupboard is bare. If that's the case, we might be living in a quiet period between outbursts. Now let's talk about the famous double nucleus mystery. When you look at high-resolution images of Andromeda's core, it appears to have two bright spots instead of one. For years, this was interpreted as evidence of a double black hole system, perhaps the result of a past merger where Andromeda consumed another galaxy along with its central black hole. The two black holes would then orbit each other at the galaxy's center, gradually spiraling inward until they eventually merge. But more detailed observations revealed the truth is more subtle. There is only one black hole at the center. The double appearance is an optical illusion created by dust. One of the bright spots is the true galactic nucleus, where the black hole sits. The other is a dense cluster of stars slightly offset from the center, and the dust distribution in that region makes it appear brighter than it actually is when viewed from our angle. So while the double nucleus looked dramatic and exciting, the reality is more mundane. However, this doesn't mean Andromeda hasn't experienced black hole mergers. The galaxy's violent history of consuming other galaxies almost certainly means it has merged with other black holes in the past. When two galaxies collide, their central black holes sink toward the center of the merged system and eventually coalesce. This process releases enormous amounts of energy in the form of gravitational waves, ripples in space-time that propagate outward at light speed. Unfortunately, these mergers happened so long ago that the gravitational waves have long since passed us, and we have no way to detect them now. Let's imagine what it would be like to live near Andromeda's core. The density of stars there is millions of times higher than in our region of the Milky Way. If you lived on a planet orbiting a star near the galactic center, your night sky would never get truly dark. Even at midnight, the combined light of billions of nearby stars would create a permanent twilight bright enough to see by without artificial light. There would be no constellations as we know them because the stars would be too numerous and too close together to form recognizable patterns. And those stars would be moving. Near the galactic center, stars orbit at tremendous speeds, sometimes hundreds of kilometers per second. They pass within light weeks or even light days of each other, close enough that gravitational interactions are common. These encounters can alter orbits, fling stars outward at high velocities, or in rare cases, cause actual collisions. When two stars collide, they merge into a single larger star, or, if the impact is violent enough, explode in a burst of energy. The environment near the black hole itself is even more extreme. Within a few light years of the event horizon, stars orbit at a significant fraction of light speed. Time dilation effects become noticeable. A clock on a planet near the black hole would run measurably slower than a clock farther out in the galaxy. If you could somehow survive near the black hole and then travel back to the outer galaxy, you'd find that more time had passed for everyone else than for you. You'd have aged more slowly thanks to relativity. The gravitational forces near the black hole are also intense enough to shred anything that gets too close. There's a boundary called the tidal radius, where the difference in gravitational pull between the near and far sides of an object becomes so large that the object is torn apart. For a star, this radius is actually quite close to the black hole, typically within a few times the event horizon, but for a planet or smaller body, it could happen much farther out. Any planet unfortunate enough to pass too close would be stretched and ripped apart, its material forming a stream that spirals into the black hole. These tidal disruption events produce bright flares that we can detect from millions of light years away. Andromeda probably experiences them occasionally, though we haven't caught one in the act yet. When a star gets shredded, its gas heats to millions of degrees and shines intensely in X-rays for months or years before disappearing into the black hole. Future monitoring programs hope to catch one of these events in Andromeda, giving us a chance to study how supermassive black holes feed in real time. The process of a tidal disruption is both beautiful and violent. As a star approaches the black hole, the tidal forces begin to stretch it. At first, the distortion is minor. But as it gets closer, the star becomes noticeably elongated, shaped more like a football than a sphere. Closer still, and the star is stretched into a long strand, like spaghetti. Astronomers actually call this spaghettification, which sounds whimsical but describes a genuinely terrifying process. Once the star is torn apart, roughly half of its material has enough energy to escape. This material flies away from the black hole at high speed, forming an expanding cloud. The other half doesn't have enough energy to escape. It falls back toward the black hole, forming an accretion disk, a swirling ring of gas spiraling inward. As this gas spirals, friction heats it to millions of degrees, causing it to glow brightly in X-rays and ultraviolet light. The brightness of this flare can increase by factors of thousands or even millions compared to the black hole's quiet state. For months or years, the black hole shines like a beacon, visible across millions of light years. Then, as all the disrupted material either escapes or falls in, the flare fades and the black hole returns to its quiet state. These flares are how we've discovered many supermassive black holes that are otherwise too dim to detect. The environment around Andromeda's black hole also includes what astronomers call the nuclear star cluster, a dense concentration of stars within the central few light years. This cluster contains millions of stars, making it one of the densest stellar environments in the galaxy. The stars here are on chaotic orbits, moving at high speeds, passing close to each other and to the black hole. Some of these stars are on highly elliptical orbits that take them very close to the black hole during their closest approach, then swing them far out before returning. These stars experience extreme variations in gravitational force over their orbits. During closest approach, they're moving at a significant fraction of light speed, experiencing strong relativistic effects. Then they swing outward, slow down, and eventually fall back in for another pass. The study of these orbits has been crucial for confirming the black hole's mass. By tracking individual stars over years or decades, astronomers can measure their orbital periods and distances. Using Newton's laws of gravity, or more accurately Einstein's general relativity, they can then calculate how much mass must be present at the center to produce these orbits. The answer is always the same: about 100 to 200 million solar masses, all concentrated in a region too small to be anything other than a supermassive black hole. The core of Andromeda is also where the oldest stars in the galaxy reside. These stars formed billions of years ago when the galaxy was young, and they've been orbiting the center ever since. They're metal poor compared to younger stars, containing fewer heavy elements because they formed from gas that hadn't been enriched by as many previous generations of stars. By studying these ancient stars, astronomers can learn about the early history of Andromeda, what conditions were like when it first formed, and how it has evolved over cosmic time. One particularly interesting class of stars found near galactic centers are called hypervelocity stars. These are stars that have been flung out of the galactic center at speeds high enough to escape the galaxy entirely. How does this happen? The most common mechanism involves binary star systems. Imagine a binary pair of stars orbiting each other. If this pair wanders too close to the supermassive black hole, the black hole's gravity can capture one star while flinging the other away at tremendous speed. The captured star falls into an orbit around the black hole, while its former companion gets launched into intergalactic space at speeds of thousands of kilometers per second. We've detected several hypervelocity stars in the Milky Way that appear to have originated from near the galactic center. Similar stars probably exist in Andromeda, though they're harder to detect because they're so far away. These stars carry information about the central black hole's mass and the dynamics of the nuclear star cluster, making them valuable probes of conditions near the galactic center. In a way, The galactic center is a time capsule. The oldest structures and stars cluster there, while the disk is constantly being renewed with fresh star formation. If you could map the age of stars throughout Andromeda, you'd find a gradient with the oldest stars concentrated in the core and progressively younger stars as you move outward into the spiral arms. This pattern tells the story of how the galaxy grew, starting as a dense central bulge and gradually building its disk through the accretion of gas and the merger of smaller galaxies. The relationship between Andromeda and its central black hole is also intimate in another way. Observations of other galaxies show a tight correlation between black hole mass and the properties of the galactic bulge. Larger bulges have more massive black holes, a relationship that holds across a wide range of galaxy sizes and types. This correlation suggests a deep connection, a feedback mechanism where the black hole's growth affects the galaxy and the galaxy's evolution affects the black hole. When a black hole feeds actively, it releases enormous amounts of energy, heating the surrounding gas and blowing it away. This can shut down star formation in the central regions of a galaxy, regulating its growth. Over billions of years, this feedback may explain why supermassive black holes don't grow indefinitely. They reach a size where their energy output prevents more matter from falling in, creating a natural equilibrium. For Andromeda, this feedback process has been operating for over 10 billion years. The black hole grew as the galaxy grew, fed by gas from the early universe and from mergers with other galaxies. Each merger added mass to both the galaxy and the black hole. And each period of active feeding regulated how fast the galaxy could form new stars. The result is the system we see today, a massive galaxy with a massive but currently quiet black hole, the product of billions of years of coevolution. This same feedback loop explains why Andromeda's central bulge looks the way it does today. The black hole's past outbursts pushed gas away from the core, slowing star formation there while letting the outer disk keep building new stars. The result is a galaxy with a pronounced older bulge and a younger, still active disk, a pattern we see in many large spirals, but especially clear in Andromeda because we can watch it from the outside. This balance between destruction and creation is what keeps galaxies from burning out too quickly, letting them live for trillions of years instead of mere billions. The future of Andromeda's black hole is also tied to the collision with the Milky Way. When the two galaxies merge, their central black holes will eventually sink to the center of the merged system and coalesce. This merger will create gravitational waves detectable across the universe, though we won't be around to witness it. The combined black hole will weigh between 100 and 200 million solar masses, making it one of the most massive black holes in the local universe. The core of Andromeda is also where the oldest stars in the galaxy reside. These stars formed billions of years ago when the galaxy was young, and they've been orbiting the center ever since. They're metal poor compared to younger stars, containing fewer heavy elements because they formed from gas that hadn't been enriched by as many previous generations of stars. By studying these ancient stars, astronomers can learn about the early history of Andromeda, what conditions were like when it first formed, and how it has evolved over cosmic time. The nuclear star cluster itself is a relic of Andromeda's earliest days. The stars there formed when the galaxy was still a chaotic cloud of gas before it had settled into a proper disk. Many of them are extremely metal poor, preserving the chemical fingerprint of the universe when it was only a few billion years old. By studying their light, we're effectively reading a diary written in the first chapters of Andromeda's life, a diary the Milky Way's own core keeps as well, but one we can read more easily in our Neighbour, because we're looking straight at it instead of from the inside. The relationship between Andromeda and its central black hole is also intimate in another way. Observations of other galaxies show a tight correlation between black hole mass and the properties of the galactic bulge. Larger bulges have more massive black holes, a relationship that holds across a wide range of galaxy sizes and types. This correlation suggests a deep connection, a feedback mechanism where the black hole's growth affects the galaxy and the galaxy's evolution affects the black hole. When a black hole feeds actively, it releases enormous amounts of energy, heating the surrounding gas and blowing it away. This can shut down star formation in the central regions of a galaxy, regulating its growth. Over billions of years, this feedback may explain why supermassive black holes don't grow indefinitely. They reach a size where their energy output prevents more matter from falling in, creating a natural equilibrium. For Andromeda, this feedback process has been operating for over 10 billion years. The black hole grew as the galaxy grew, fed by gas from the early universe and from mergers with other galaxies. Each merger added mass to both the galaxy and the black hole. And each period of active feeding regulated how fast the galaxy could form new stars. The result is the system we see today, a massive galaxy with a massive but currently quiet black hole, the product of billions of years of co-evolution. Here's something remarkable about Andromeda. It's the only large spiral galaxy we can see almost face-on. Most galaxies are so far away that we see them at random angles, often edge-on or tilted, making it difficult to study their structure in detail. But Andromeda is tilted at just the right angle, close enough and oriented correctly, that we can map its spiral arms, dust lanes, star-forming regions, and halo with incredible precision. This makes it the perfect laboratory for understanding spiral galaxies in general, including our own Milky Way. Think of Andromeda as a cosmic mirror. When we study it, we're learning about the kind of galaxy we live in. The Milky Way is also a large spiral, similar in many ways to Andromeda. But there's a fundamental problem with studying your own galaxy. You're embedded in it. You're looking at it from the inside, surrounded by stars and dust that block your view of distant regions. Mapping the Milky Way's structure is like trying to understand the layout of a city while standing in the middle of a crowded street. It's possible, but difficult. With Andromeda, we have an outside view. We can see the entire structure laid out in front of us. We can trace the spiral arms from the core to the outer edges. We can map where stars are forming and where they're dying. We can identify tidal streams and measure the distribution of dark matter. All of this teaches us about how spiral galaxies work, and we can then apply those lessons to understanding our own galaxy. But here's where the mirror analogy becomes interesting. The mirror is cracked. Andromeda and the Milky Way are similar, but they're not identical. Andromeda has been through a much more violent history. It suffered a major merger 2 to 4 billion years ago, something the Milky Way managed to avoid. During this merger, another large galaxy, possibly a third or half the mass of Andromeda, collided and merged with it. The impact disrupted the disk, triggered enormous bursts of star formation, and fundamentally changed Andromeda's structure. We can see evidence of this ancient merger everywhere in Andromeda. The thick, irregular dust lanes are one sign. In an undisturbed spiral galaxy, dust lanes follow neat spiral patterns. But in Andromeda, they're chaotic, twisted, showing that something major disrupted them. The giant stellar streams in the halo are another sign. And the high rate of star formation we mentioned earlier is a direct consequence of that merger. The collision compressed gas clouds throughout the galaxy, triggering star formation that continues even now, billions of years later. The Milky Way, by contrast, has had a relatively peaceful history. We've consumed many small dwarf galaxies, but we haven't experienced a major merger with another large galaxy for at least 10 billion years. This makes our galaxy's structure cleaner, more organized, less scarred by ancient violence. In a way, Andromeda shows us what the Milky Way might look like if we'd had a more turbulent past. One of the most fascinating recent discoveries comes from the FANG's JWST program, a survey using the James Webb Space Telescope to map star formation in nearby galaxies. The 2025 images of Andromeda from this program reveal something unexpected. Star formation is happening in perfect rings, circular structures where new stars are being born in coordinated waves. These rings are rare in spiral galaxies, and the Milky Way doesn't have them anymore, though we might have in the distant past. The rings form through a process called resonance. As the galaxy rotates, density waves sweep through the disk at specific speeds. At certain distances from the center, the rotation rate of the disk matches the rotation rate of the density wave, creating a resonance. Gas piles up at these resonance locations, gets compressed, and forms stars. The result is a ring of star formation encircling the galactic center. Picture it like pushing a child on a swing. If you push at just the right frequency, matching the swing's natural rhythm, the motion gets amplified. That's resonance. In Andromeda, the density waves and the disk rotation are matched at specific radii, creating these rings where gas accumulates and star formation explodes. Why does Andromeda still have these rings while the Milky Way doesn't? The answer probably lies in that ancient merger. The collision disrupted Andromeda's disk in ways that set up the conditions for resonance rings to form. The Milky Way's disk, being more settled and less disturbed, doesn't have the right structure to sustain them. This is another example of how Andromeda's violent past continues to shape its present. Another striking feature visible in detailed images is that the southern half of Andromeda's disk looks more disturbed than the northern half. The spiral arms are less well defined, the star-forming regions are more chaotic, and there's more evidence of tidal damage. This asymmetry suggests that the ancient merger approached from one side, impacting the southern regions more severely. Even after billions of years, the galaxy is still healing from that encounter, still settling back into equilibrium. Galaxies are remarkably resilient. Even after catastrophic collisions, they don't fly apart. Gravity reassembles them, pulling scattered stars and gas back together, forming new structures. But the healing process takes time, billions of years, and Andromeda is still in the middle of it. When we look at Andromeda, we're seeing a galaxy in recovery, still bearing the scars of ancient battles, but slowly, inexorably, returning to a more stable configuration. This makes Andromeda an invaluable resource for astronomers studying galaxy evolution. We can observe different parts of the galaxy in different stages of recovery. Some regions have healed more completely, while others still show fresh damage. By comparing these regions, we can learn how long it takes for a galaxy to settle after a major merger and what processes drive that settling. The comparison between Andromeda and the Milky Way also extends to their satellite galaxies. Both have dozens of small companions, but the distributions are different. Andromeda's satellites, as we discussed, show that strange planar structure. The Milky Way's satellites also show some organization, but not as pronounced. This suggests that the formation and evolution of satellite systems is more complex than simple models predict, and studying both galaxies helps us refine our understanding. Now we come to the part everyone secretly wants to hear about, the collision. Because Andromeda isn't just sitting there in space, it's moving, and it's moving toward us. This was confirmed decades ago when astronomers first measured Andromeda's motion through space and realized it was the only major galaxy with a clear blue shift, meaning it's approaching rather than receding. At first, this seemed odd. Almost every distant galaxy shows a redshift because the universe is expanding, carrying them away from us. But Andromeda's gravity is strong enough to overcome that expansion at our local scale. It's pulling the Milky Way toward it, and we're pulling Andromeda toward us, and the gap between us is closing. For years, there was uncertainty about exactly what would happen. Would the galaxies collide directly, or would they miss each other and pass by harmlessly? The challenge is that we can easily measure how fast Andromeda is approaching, but measuring its sideways motion, its tangential velocity, is much harder. That requires incredibly precise measurements over many years to detect tiny shifts in position against the background of more distant galaxies. The latest measurements from 2025 have finally nailed down Andromeda's tangential velocity with enough precision to make solid predictions. The latest 2020-25 measurements using Gaia and JWST data have dramatically lowered the uncertainty a direct collision is now considered almost certain, with only a very small chance the galaxies will merely graze each other. If it does happen, the first close pass will occur in approximately 4.3 billion years. That's a few 100 million years earlier than some older estimates. During this first pass, the two galaxies won't merge immediately. They'll sweep through each other, their stars passing by harmlessly because the distances between individual stars are so vast. Even in a dense galactic collision, actual star-on-star impacts are incredibly rare. Think about the scale involved. The closest star to our Sun is over 4 light-years away. That's about 25 trillion miles. In Andromeda, the spacing is similar. So when the galaxies collide, it's not like two solid objects smashing together. It's more like two swarms of bees flying through each other. The individual bees, the stars, almost never collide, but the overall structures of the swarms get disrupted. But even though the stars don't collide, the galaxies are profoundly affected. Their shapes get distorted by tidal forces. Long tails of stars get pulled out from each galaxy, streaming millions of light-years into space. These tidal tails are common in colliding galaxies and have been observed in many systems throughout the universe. They're beautiful, dramatic, and a clear sign of gravitational chaos. Let's talk about what Earth's night sky will look like during this encounter. Assuming Earth and the solar system still exist, which is questionable for other reasons we'll get to, the view would be extraordinary. Right now, Andromeda appears as a small, faint smudge, but as it approaches, it will grow larger and brighter. By the time it's 1 billion years away from first contact, Andromeda will span several degrees across the sky, larger than the full moon, a spectacular sight for any astronomers lucky enough to witness it. As the approach continues, Andromeda will grow to dominate the night sky. Eventually, it will stretch across dozens of degrees, filling half the heavens with its spiral structure. You'd be able to see individual star clusters within it with the naked eye. The dust lanes would be visible as dark rifts cutting across glowing regions. And the whole structure would have a three-dimensional appearance because you'd be looking at it from so close. When the galaxies finally interpenetrate during the first pass, the night sky becomes something out of a science fiction film. Andromeda's disk would stretch from horizon to horizon. Our own galaxy's stars would be mixed with Andromeda's. There would be no clear distinction between which stars belong to which galaxy. The entire sky would glow with billions of stars, some from the Milky Way, some from Andromeda, all jumbled together in a cosmic collision. And this is just the first pass. After the galaxies sweep through each other, they don't separate cleanly. Gravity pulls them back together. They orbit around their common center of mass, spiral inward, and collide again and again. Each passage brings them closer, strips away more energy, and mixes their structures more thoroughly. This process continues over about 2 billion years, with multiple passes until the two galaxies finally merge completely. During these collisions, star formation explodes. Gas clouds from the two galaxies smash into each other, compressing and triggering massive bursts of star birth. Starburst rings form. glowing circles of new stars surrounding the merging cores. These starbursts can increase the star formation rate by factors of 10 or more, creating millions of massive, bright stars that light up the combined system. The reason for this burst is simple. When two gas clouds collide, they compress each other, and compressed gas collapses more easily under its own gravity. So regions that might have taken millions of years to form stars in isolation can collapse in just thousands of years when compressed by a collision. The result is an explosion of star formation, creating some of the most massive and luminous stars possible. But let's think about what's actually happening during these collisions in more detail. The gas clouds in both galaxies are moving at hundreds of kilometers per second. When they collide, it's not a gentle encounter. The kinetic energy of the collision gets converted into heat and compression. The temperature of the gas spikes to millions of degrees in the shock fronts where the clouds meet. Behind these shock fronts, the compressed gas cools rapidly and density increases dramatically. This creates ideal conditions for star formation. The compressed, dense gas fragments into thousands of clumps, each one massive enough to collapse under its own gravity. Within a few million years, these clumps ignite as new stars. The most massive stars, weighing dozens of times what the Sun weighs, burn incredibly hot and bright. They emit so much ultraviolet radiation that they ionize the surrounding gas, creating vast glowing nebulae visible across millions of light years. These starburst regions are some of the most spectacular sights in the universe. If you could see them up close, you'd witness thousands of massive young stars clustered together, each one blazing with the light of millions of suns. The surrounding gas would glow in brilliant reds, blues, and greens, each color corresponding to different elements being ionized by the starlight. Hydrogen glows red, oxygen glows green, and sulfur glows blue. The combination creates a rainbow of colors that's both beautiful and scientifically informative. But starbursts are also destructive. The massive stars don't live long. Within just a few million years, they exhaust their fuel and explode as supernovas. These explosions blast the surrounding gas at thousands of kilometers per second, creating expanding bubbles of superhot plasma. Multiple supernovas can overlap, creating superbubbles hundreds or even thousands of light years across. These superbubbles can actually blow gas completely out of the galaxy, carrying it into intergalactic space where it might never return. This galactic wind, as astronomers call it, is a crucial part of galaxy evolution. It regulates star formation by removing the raw material needed to make new stars. Without galactic winds, galaxies would convert all their gas into stars very quickly, then go dark as star formation shut down completely. But with winds, the process is more gradual. Some gas gets expelled, some remains to form new stars, and the galaxy maintains a steady rate of star formation over billions of years. The two galactic cores, each containing a supermassive black hole, spiral toward each other. As they get closer, they orbit faster, dozens or hundreds of times per second in the final moments before merging. The energy released when they finally coalesce is staggering. The merger creates gravitational waves so powerful they would be detectable across billions of light years. Unfortunately, since this won't happen for billions of years, we won't be around to detect them. But future civilizations somewhere in the universe might catch the signal and know that two galaxies merged in this corner of the cosmos. The merger of two supermassive black holes is one of the most energetic events in the universe. More energy is released in gravitational waves in the final seconds than all the stars in both galaxies produce in light over the same period. The space-time around the black holes gets violently distorted, and the gravitational waves propagate outward at light speed, stretching and compressing space as they pass. Let's imagine what it would be like to observe this from a safe distance. As the black holes spiral together, they emit gravitational waves that carry away energy and angular momentum. This causes their orbit to decay, bringing them closer and closer together. In the final hours, they're orbiting each other dozens of times per second, separated by only a few times their event horizons. The space-time around them is incredibly warped, creating a complex pattern of gravitational lensing that would distort the appearance of background stars and galaxies. Then, in the final seconds, they merge. The two event horizons touch, merge into one, and the combined black hole settles into its final state. The newly formed black hole vibrates like a ringing bell, emitting gravitational waves that gradually decay as it settles down. Within minutes, the merger is complete, and a single, larger black hole remains where two once existed. The gravitational waves from this merger carry information about the masses and spins of the original black holes. By detecting these waves with instruments like LIGO or future space-based detectors, astronomers can learn about the properties of supermassive black holes in distant galaxies. This field, called gravitational wave astronomy, is revolutionizing our understanding of the universe's most violent events. After all the chaos settles, what's left is a single giant elliptical galaxy. The spiral structure of both galaxies is destroyed. The ordered rotation of the disks is disrupted into random stellar orbits. The result is a blob, for lack of a better term, a roughly spherical distribution of stars with no clear structure. Astronomers have given this future merged galaxy a playful name: Milkomeda, a blend of Milky Way and Andromeda. Milkomeda will be enormous, containing perhaps 1.5 to 2 trillion stars, the combined population of both galaxies, minus some that get flung into intergalactic space during the collision. It will be one of the largest galaxies in the local group, and it will continue to grow by consuming the remaining dwarf galaxies in the neighborhood. The Triangulum galaxy, currently the third largest member of the local group, will likely be absorbed into Milkomeda as well, though the exact timing and trajectory are uncertain. The structure of Milkomeda will be very different from the spiral galaxies that formed it. Elliptical galaxies have little organized rotation. Instead, stars move on complex, chaotic orbits that take them in all directions. Some orbits are nearly circular, while others are highly elongated. The overall shape is determined by the collective motion of all these stars, which creates a roughly elliptical or spherical structure. Elliptical galaxies also have very little gas left. Most of the gas gets consumed in the starburst during the merger, converted into stars. The rest gets blown away by supernova explosions and galactic winds. Without gas, new star formation shuts down almost completely. Elliptical galaxies are sometimes called red and dead because they contain mostly old, red stars with almost no young, blue stars being born. This doesn't mean Milkomeda will be lifeless. It will still contain trillions of stars, many with planetary systems, some of those planets potentially harboring life. But the galaxy itself will be slowly aging, gradually fading as its stars exhaust their fuel and die. Over hundreds of billions of years, the brightest stars will burn out first, leaving behind white dwarfs, neutron stars, and black holes. Eventually, only the smallest, longest-lived stars will remain, glowing faintly in the darkness. Now, what about Earth and the solar system during all this? Here's where things get both reassuring and concerning. The reassuring part is that the collision itself is unlikely to directly harm us. Stars are so far apart that even when two galaxies merge, individual stars almost never collide. The Sun will probably pass through the chaos unscathed, and Earth will continue orbiting as it always has. However, and this is the concerning part, the Sun will likely be flung to the outer regions of Milkomeda. During the merger, gravitational interactions between stars can change orbits dramatically. Some stars get pulled toward the center of the merged galaxy. Others get flung outward, sometimes with enough energy to escape the galaxy entirely. Computer simulations suggest the Sun has a reasonable chance of ending up in the outer halo of Milkomeda, far from the dense central regions. Being in the outer halo isn't necessarily bad. It's actually quieter and less hazardous than being near the core. But it means that if humanity, or whatever descends from humanity, is still around, they'll find themselves in a very different neighborhood. The familiar Milky Way will be gone, replaced by a structureless, elliptical galaxy. The night sky, if Earth still has one, will be different, filled with distant stars but lacking the dense band of light we associate with our galaxy's disk. The night sky from Earth during and after the merger would be genuinely spectacular. During the collision, the sky would be filled with stars from both galaxies. You'd see massive starbursts, glowing nebulae, and perhaps even supernova explosions visible to the naked eye. The combined light might be bright enough that true darkness never falls, creating a permanent twilight even at midnight. After the merger is complete and the Sun has been flung to the outer halo, the night sky would be quieter, but still remarkable. You'd see the bright core of Milkomeda in one direction, a massive concentration of stars that would never set, always visible above the horizon. In other directions, you'd see a sparser distribution of halo stars, along with the satellite galaxies that orbit Milkomeda and the more distant galaxies beyond our local group. And there's another complication. Even if Earth survives the collision, it might not survive the Sunday. In about 5 billion years, the Sun will exhaust the hydrogen in its core and begin evolving into a red giant. It will swell to perhaps 100 times its current size, possibly large enough to engulf Earth's orbit. Whether Earth is consumed or merely baked to a lifeless cinder is uncertain, but either way, the planet will be uninhabitable long before the collision with Andromeda is complete. This timeline means that any observers of the Milky Way Andromeda collision will not be on Earth. They'll either be on another planet in another star system, having left Earth billions of years ago, or they'll be something we can't even imagine. Descendants of humanity evolve beyond recognition. Artificial intelligences, digital consciousnesses uploaded into machines. Or perhaps biological entities so modified by genetic engineering that they bear little resemblance to humans as we know them today. But whoever or whatever they are, they'll get to witness one of the most spectacular events in cosmic history. The collision of two giant spiral galaxies, the birth of trillions of new stars, the merger of two supermassive black holes, and the formation of a new galaxy that will dominate the local group for hundreds of billions of years to come. So realistically, any observers of the Milky Way Andromeda collision will either be on a different planet, having left Earth billions of years ago, or they'll be something we can't even imagine, descendants of humanity evolved beyond recognition, or perhaps artificial intelligences, or something else entirely. But the collision will be observable, and it will be spectacular. The fact that the collision is gentle on planetary systems is worth emphasizing. Popular depictions sometimes show galaxies colliding with massive explosions and widespread destruction. But the reality is more subtle. Yes, the large-scale structure gets disrupted. Yes, star formation explodes. But for any individual star and its planets, life continues much as before. The night sky changes dramatically, but the sun keeps shining, the planets keep orbiting, and if anyone is watching, they get to witness one of the most spectacular events in the universe. There's also the possibility that the collision will create conditions more favorable for life in some regions. The burst of star formation will create millions of new planetary systems. Some of those planets will be inhabitable zones around their stars. And the enrichment of the interstellar medium with fresh elements from the starburst could provide excellent raw materials for the formation of complex chemistry and life. In a sense, the collision is both an ending and a beginning. It's the end of the Milky Way and Andromeda as separate entities. But it's the beginning of Milkomeda, a new galaxy with new possibilities. And throughout the process, the cycle of stellar birth and death continues. Stars form, live, and die, and the universe keeps evolving. But there's something deeper worth considering about this collision. It represents a pattern that plays out across the entire universe at every scale over all of cosmic time. Galaxies don't exist in isolation. They interact, they merge, they evolve together. And this process of merger and transformation is actually how the universe builds complexity. Think about it. In the early universe, just a few 100 million years after the Big Bang, there were no large galaxies like Andromeda or the Milky Way. There were only small proto-galaxies, fragments containing perhaps a few million stars each. Over billions of years, these fragments collided and merged, building progressively larger structures. Every large galaxy we see today, including Andromeda, is the product of countless mergers stretching back to the cosmic dawn. The collision between Andromeda and the Milky Way is part of this ongoing process. We're witnessing, or will witness, one more step in the hierarchical assembly of structure in the universe. Small things combine to make bigger things, and those bigger things eventually combine to make even larger structures. It's happening at every level, from the formation of stars from gas clouds, to the formation of galaxies from merging fragments, to the formation of galaxy clusters from colliding galaxies. What makes our particular merger special is that we can predict it, study it in advance, and understand what will happen. We can't watch the merger itself because it won't occur for billions of years. But we can observe similar mergers happening in distant galaxies right now. When we look at colliding galaxies across the universe, we're seeing previews of our own future. We're watching what will happen to us, played out on cosmic stages millions of light years away. One of the most famous examples is the antennae galaxies, two spirals caught in the act of merging about 60 million light years from Earth. Their collision has pulled out two long tidal tails that stretch across hundreds of thousands of light years, looking like the antennae of an insect, hence the name. The cores of the two galaxies are still distinct, but they're spiraling closer together, and in a few 100 million years they'll merge completely. The starburst triggered by their collision is visible even from this enormous distance, with billions of new stars forming in the compressed gas between the colliding disks. Another example is the mice galaxies, named for their long tails that resemble the tails of mice. These galaxies passed through each other about 290 million years ago, and they're currently swinging back for another pass. Eventually, they'll merge completely, but for now, they're still dancing around each other, their structures heavily distorted by tidal forces. These observations tell us what to expect from the Andromeda-Milky Way collision. We can see the stages it will go through, the structures it will create, and the final product that will emerge. This predictive power is one of astronomy's greatest achievements. We can look billions of years into the future and know, with reasonable certainty, what will happen to our cosmic neighborhood. And here's the remarkable part. Even after the collision, even after Milkomeda forms and settles into its final elliptical shape, the story doesn't end. Milkomeda will continue to interact with other galaxies in the local group. It will continue to consume dwarf galaxies, and eventually, on timescales of hundreds of billions of years, it might even merge with other large galaxies if they happen to be on collision courses. The process never truly stops. It just continues at larger and larger scales, building ever more massive structures over cosmic time. As we come to the end of this journey through Andromeda's secrets, let's step back and consider what we've learned. Andromeda is massive, containing over 1 trillion stars, twice as wide as we thought just a few years ago. It's violently active, forming stars at several times the rate of the Milky Way, still recovering from ancient collisions that tore through its structure billions of years ago. It's surrounded by a halo of dark matter and the ghostly remains of consumed galaxies, dozens of satellite systems orbiting like moths around a flame, some doomed to be absorbed in the future. At its heart sits a supermassive black hole, quiet now, but capable of tremendous violence, surrounded by some of the densest stellar environments we can observe. And it's approaching us, pulled by gravity across millions of light years, on a collision course that will play out over billions of years and reshape both galaxies completely. But here's something worth holding on to. Every atom in Andromeda was forged in the same way as the atoms in the Milky Way, in the hearts of stars, in supernova explosions, in the collisions of neutron stars. The elements that make up Andromeda's stars and planets are the same elements that make up our bodies. We are, quite literally, built from the same ancient atoms. There's a deep connection between us and that distant galaxy, a kinship written in the periodic table. The hydrogen that's so abundant in Andromeda, making up most of its gas clouds and most of its stars, is the same hydrogen that flows through your body right now in water molecules, in organic compounds, in every cell. That hydrogen has existed since the Big Bang, cycling through stars, through space, through planets, through living things for nearly 14 billion years. Some of the hydrogen atoms in your body might have once been part of a star in a galaxy that Andromeda consumed billions of years ago. The cosmic recycling program is that thorough. Think about that journey for a moment. A hydrogen atom forms in the first few minutes after the Big Bang, when the universe is incredibly hot and dense. As the universe expands and cools, that atom drifts through space for millions of years, part of the primordial gas that fills the early universe. Eventually, it gets pulled into a forming galaxy, perhaps a small dwarf that will one day be consumed by Andromeda. Inside that dwarf galaxy, the hydrogen atom becomes part of a gas cloud. The cloud collapses under its own gravity, and the atom finds itself inside a star. For millions or billions of years, it's part of the star's outer layers, slowly circulating through the stellar interior. Eventually, the star dies, either gently puffing off its outer layers or violently exploding as a supernova. The hydrogen atom is ejected back into space. It drifts through the dwarf galaxy for millions more years, until the dwarf falls into Andromeda. The merger disrupts the gas, and the atom becomes part of Andromeda's interstellar medium. It floats through the larger galaxy for billions of years, occasionally becoming part of new stars, getting ejected again, cycling through the galactic ecosystem. Fast forward to 4.5 billion years ago. The Milky Way and Andromeda are approaching each other, though they won't collide for billions more years. But gas is already being exchanged between the galaxies, pulled out by tidal forces. The hydrogen atom finds itself in one of these tidal streams, bridging the gap between the two galaxies. Eventually, it falls into the Milky Way. Once in the Milky Way, the atom becomes part of a molecular cloud in one of the spiral arms. That cloud collapses to form a new star, our Sun, along with a disk of material that will become planets. The hydrogen atom ends up in a water molecule on the young Earth. For billions of years, it cycles through Earth's oceans, atmosphere, rocks, and living organisms. And today, right now, it's part of you. That's the journey of a single atom. Multiply that by the septillions of atoms in your body, each with its own unique history, and you begin to understand the depth of our connection to the cosmos. We're not separate from the universe. We're thoroughly integrated into it, part of the same cycling of matter and energy that's been operating since the beginning. If anyone lives in Andromeda, if intelligent civilizations have arisen on planets orbiting those trillion stars, they would look up at their night sky and see the Milky Way. They would see us as a beautiful spiral, a faint smudge of light in their constellations, exactly as we see them. The light they observe would be ancient, showing the Milky Way as it was millions of years ago, just as we see Andromeda in its past. We're looking at each other across time and space, two galaxies bound by gravity and history. And here's a thought that should take your breath away. If there are astronomers in Andromeda studying the Milky Way right now, they're seeing our galaxy as it was 2.5 million years ago. They're seeing stars that might have died since then. They're seeing a galactic structure that might have changed. And if they could detect individual events, they might be seeing the moment when our ancestors first appeared on Earth. The light carrying that information is reaching them right now, traveling across the void at light speed, bringing news of our origin to distant observers. They might be watching as early hominids descend from the trees and begin walking upright on the African savanna. They might be observing the spread of early humans across continents, the development of agriculture, the rise of civilizations, all delayed by 2.5 million years, compressed into a time-lapse viewed from across the cosmos. And if they could somehow send a message to us, we wouldn't receive it for another 2.5 million years. By then, who knows what humanity will have become. This time delay creates a strange kind of cosmic isolation. We can see Andromeda, study it in detail, learn about its structure and history, but we're always seeing it as it was, never as it is. There's no way to know what's happening there right now. For all we know, a supernova might have exploded in Andromeda yesterday, a spectacular event that won't be visible from Earth for another 2.5 million years. Andromeda is the only galaxy whose individual stars we can study in detail outside our own. With powerful telescopes, we can resolve individual red giants, supergiants, and variable stars in Andromeda's disk. We can measure their properties, determine their ages, and learn about stellar evolution in an environment outside the Milky Way. This makes Andromeda our cosmic twin, a companion system where we can test our theories about how stars and galaxies work. One class of stars that's particularly useful for studying Andromeda is Cepheid variables. These are massive stars that pulsate regularly, brightening and dimming with periods ranging from days to months. The remarkable thing about Cepheids is that their pulsation period is directly related to their intrinsic brightness. A Cepheid that pulsates every 10 days is intrinsically brighter than one that pulsates every 3 days. This relationship allows astronomers to use Cepheids as standard candles, measuring their apparent brightness and comparing it to their known intrinsic brightness to calculate distance. This is actually how Edwin Hubble determined a distance to Andromeda in the 1920s. He identified Cepheid variables in Andromeda, measured their periods and apparent brightnesses, and calculated that the galaxy must be about 900,000 light-years away. This was far beyond the known size of the Milky Way, proving that Andromeda was a separate galaxy and not just a nebula within our own. His estimate was too low by modern standards. We now know Andromeda is about 2.5 million light-years away, but it was close enough to demonstrate that the universe was far larger than anyone had imagined. The comparison has taught us so much. By studying Andromeda, we've learned how spiral galaxies grow through mergers, how supermassive black holes feed and sleep, how dark matter halos extend far beyond visible structures, and how galactic collisions trigger bursts of creation even as they destroy old orders. We've seen what violence looks like on cosmic scales and learned that galaxies are resilient, that they heal, that they endure. We've also learned about the diversity of stellar populations. Andromeda contains stars of all ages, from ancient red giants that formed over 10 billion years ago to massive blue stars that ignited just a few million years ago. By studying these populations in detail, astronomers can reconstruct Andromeda's star formation history, determining when and where different generations of stars were born. This star formation history tells a story of episodic growth. Andromeda didn't form all its stars at once. Instead, star formation proceeded in bursts, with periods of intense activity followed by quieter intervals. The bursts correspond to mergers with other galaxies. Each time Andromeda consumed a companion, the collision compressed gas and triggered massive star formation. The quiet periods are when the galaxy was between mergers, forming stars at a more modest rate from its remaining gas reservoirs. And we've learned about our future. The collision with Andromeda is inevitable, or at least highly probable. In 4 to 5 billion years, the local group will undergo a transformation. Two large spirals will dance together, merge, and create something new. The structures we know will be destroyed, but new structures will form. Star formation will explode. New solar systems will be born, and the combined galaxy will contain nearly 2 trillion stars, each one a sun, many with planets, some of those planets perhaps harboring life. This collision will also affect the other galaxies in the local group. The Triangulum galaxy, currently the third largest member, will likely be drawn into the chaos. It might merge with Andromeda before the Milky Way does, or it might wait until after, becoming part of Milkomeda in a later collision. The dozens of dwarf galaxies that orbit both the Milky Way and Andromeda will also be affected. Some will be disrupted by tidal forces. Others will survive, continuing to orbit the merged galaxy. This isn't an ending, it's a transformation. Galaxies don't die in collisions. They change, they evolve. And in the case of the Milky Way and Andromeda, they'll become something grander than either was alone. Milkomeda will be a giant elliptical, one of the most massive galaxies in the local universe, a monument to billions of years of cosmic evolution. But all of that is in the distant future. Right now, tonight, Andromeda sits 2.5 million light-years away, a faint smudge in the autumn sky. If you go outside after sunset, away from city lights, and find the constellation Andromeda, you can see it. You can look at another galaxy with your own eyes. You can see light that has been traveling toward you since before humans existed. And you can think about the trillion stars gathered there, the planets that surely orbit them, and the possibility that someone on one of those planets might be looking back at us, wondering the same things we wonder. The universe is vast beyond comprehension, filled with more galaxies than there are stars in the Milky Way. But Andromeda is special. It's our neighbor. It's close enough to study in detail, close enough to see as more than just a point of light, close enough that we can map its structure and predict its fate, and close enough that it will one day merge with our own galaxy, creating something new from the collision of two ancient spirals. Every atom in you was forged in stars, scattered by their deaths, and reformed into the pattern that is you. Some of those atoms might have come from stars that once existed in a galaxy Andromeda consumed billions of years ago. You are connected to Andromeda in ways you might never have imagined, part of the same cosmic story, made of the same materials, governed by the same laws of physics. And billions of years from now, when the collision is complete, the atoms that make up your body will still exist. They'll be scattered across Milkomeda, incorporated into new stars, new planets, perhaps new life. The cycle continues. Creation, destruction, and rebirth. This is how the universe works. Nothing is permanent, but nothing is truly lost. Matter and energy transform, change form, create new patterns, but they endure. The journey from the Big Bang to this moment, From the first hydrogen atoms to the complex molecules in your brain, from the first stars to Andromeda's trillion suns, it's all one continuous story. And that story is still being written. New stars are forming right now in Andromeda. New planets are coalescing from dust. And perhaps, on some of those worlds, new life is beginning its own journey of evolution and discovery. So tonight, as you look up at that faint smudge in the constellation Andromeda, remember what you're seeing. Another galaxy, a trillion stars, billions of years of history, a violent past still written in streams of scattered stars, a quiet black hole waiting in the darkness, a future collision that will reshape our cosmic neighborhood, and the possibility, however remote, that someone there is looking back, seeing our Milky Way, wondering if they're alone. You're not alone, neither are they. We're all part of the same universe, made of the same star stuff, connected across the vast darkness by gravity and light and the laws that govern everything. Andromeda is our neighbor, our mirror, our future collision partner, and our cosmic twin. And every time you look up and see it, you're looking across millions of light years and billions of years of history, seeing a galaxy that will one day merge with ours to create something new. Rest easy, knowing that the universe is vast and beautiful and full of wonders we're only beginning to understand. Andromeda is just one galaxy among trillions, but it's ours to study, to marvel at, and eventually to merge with. The light you see tonight left Andromeda before your species existed and arrived just in time for you to witness it. That's something worth remembering. The galaxies turn, the stars shine, the universe expands, and you, made of atoms forged in ancient stars, get to be here to see it all. That's the greatest secret of Andromeda. Not just that it exists, but that we exist to wonder about it. That the universe has evolved in such a way that matter can organize itself into patterns complex enough to look back at the cosmos and understand what it's seeing. Sleep well, stardust. The galaxy holds you and always will. And in that quiet embrace, remember every night you fall asleep beneath the same sky that holds Andromeda. Two galaxies, separated by millions of light years, bound together by gravity and destiny. The collision will happen, the transformation will be complete, and the universe will continue its eternal dance of creation and change. Your heartbeat, soft and steady, echoes the slow pulse of galaxies that have never stopped turning, never stopped holding you. Close your eyes now. The spiral is still here. Andromeda is still there. And you are still home, part of a cosmos so vast and so beautiful that even after billions of years of study, we've only just begun to understand its secrets. The light from Andromeda will keep traveling. New photons are leaving that galaxy right now, beginning their 2.5 million year journey toward Earth. Some of them will arrive when humanity has long since evolved into something else. Some will arrive when Earth itself has been consumed by the dying Sunday. But they'll keep coming, carrying news of a distant galaxy, until the collision finally brings Andromeda and the Milky Way together into one unified whole. And when that happens, there will be no more separation, no more distance, no more looking across the void at our cosmic neighbor. We'll be one galaxy, one system, one structure, Milkomeda. A new beginning born from the merger of two ancient histories. That's the future waiting for us, written in the motions of galaxies, inevitable as the sunrise, beautiful as the stars. Sleep now. Dream of spirals turning slowly through the dark. Dream of trillion-star galaxies approaching across the void. Dream of collision and creation, of endings that are also beginnings. And know that you are part of this story, connected to Andromeda by bonds deeper than distance, made of the same materials, following the same laws, part of the same cosmic dance that began nearly 14 billion years ago and continues still. The universe holds you, Andromeda watches over you, and somewhere in that distant spiral, perhaps someone is looking back, seeing our Milky Way, feeling the same wonder we feel when we look at them. Two civilizations, if they exist, gazing at each other across the abyss, both made of star stuff, both asking the same questions, both seeking to understand their place in the cosmos. That's the final secret of Andromeda. Not just what it is, but what it represents. The possibility of connection across impossible distances. The reality of cosmic kinship. The knowledge that we're not isolated, not separate, but part of a universe so interconnected that the atoms in your body have traveled through countless stars and galaxies before coming together in you. Sleep well, Stardust. The galaxies are turning, and you are home.